everyone, continuing with my previous video on theory of trim. I'm uploading now one past paper question from Naval Arc. It's on ambition ship. Ambition ship is at even keel draft of 9.30 meter floating in fresh water. Calculate her draft forward and aft when she goes to salt water. Assume negligible consumption of fuel and fresh water. Explain the change of trim with diagram. So this is a concept clearing question, that what happens when the density of the seawater changes. So a ship is loaded in fresh water in a river port, and the sailing draft in the river port was 9.30 meter even keel. So she sails out of the river port and enters into the open sea where the density changes to salt water. How will the trim change and forward and aft draft change? So first of all, we know very well that mass is equal to volume into density. Mass, which is the displacement, remains unchanged because only the density of the seawater is changing from fresh to salt. So if the mass remains unchanged, then density is increasing from 1 to 1.025. The underwater volume must then decrease. That means the ship's draft, hydrostatic draft, will reduce by some amount, which you can always find the freshwater allowance by the formula. So here is the extract from the hydrostatic particulars of Hinship for the range of drafts we need for calculation and the figures which are required. First, we will go through the calculation, and when on the basis of our calculation, we'll go to the diagram which they are asking to draw a diagram and explain the change of trim. Okay, draft in freshwater given in the question is 9.30 meter even keel. So since the ship is on even keel, so the hydrostatic draft is also 9.30 meter because ship is on even keel. So I enter hydrostatic particulars with 9.30 meter draft. I will get displacement in salt water at 9.30 meter, 19780.5 tons. Okay, here is the extract from the particulars. So it's here. Okay, between 9.2 and 9.4, you can interpolate for 9.3, which is exactly halfway, and you get the saltwater displacement 19780.5. So what is the displacement in fresh water? I have the displacement at 9.30 meter in salt water. So if I divide the displacement by density of salt water, I will get underwater volume at 9.30 meter. Then multiply by the density of fresh water, I will get the displacement in fresh water. So 19780.5 divided by 1.025 is the underwater volume at 9.30 meter, multiplied by the density of fresh water, which is 1 ton per cubic meter. I get displacement in fresh water, which is the actual weight, actual displacement of the vessel at 9.30 meter draft in fresh water. So I get 19298.0 tons displacement of the vessel. This is the actual displacement at which she is floating in fresh water. So if the ship is at even keel, we know that LCB must be equal to LCG. So LCB is 72.191 meter in freshwater, and you know the LCB is not affected by density. So you can just enter 9.30 meter draft. 9.30 meter draft in the particulars, even though the particulars are for salt water, but it doesn't affect the LCB. So 9.30 meter and LCB is here between 72.223 and 72.159. We interpolate for 9.3 and I get LCB 72.191, which is my LCG also. So this is my LCG when the ship sailed, and my displacement is 19298. Okay, now the ship is in salt water. She has come out of the river port and she is in salt water. Whatever small fuel consumption what may have taken place, that is to be ignored as per the question. Assume negligible consumption of fuel and fresh water, okay, between the dock and the open sea. So has my displacement changed? No. Whatever displacement I had upon departure, that is the weight of my ship, that has not changed. I have not done any operation now. Only the seawater density has changed. So the weight of the ship remains unchanged, which is the displacement. So the displacement in fresh water when at 9.30 meter draft was 19298. That remains the same. So displacement in salt water is again 19298.0. So I have the 19298.0 as a displacement in salt water. I can enter hydrostatic particulars and against 19298 displacement I can read the hydrostatic draft, which is here. So I get the draft 9.102 meter after interpolating between 19051 and 19537 here. Hydrostatic draft is 9.10 meter in salt water. LCB 72.255. LCB in salt water now is here at hydrostatic draft of 9.102 meter. Displacement of 19298. I can interpolate and I got my LCB 72.255, also MCTC 213.2 and LCF 69.688. So all from this extract here. Interpolating, either you interpolate for the displacement, which is 19298, or you interpolate for the hydrostatic draft, which is 9.102 against that displacement. You will get the same values. Now final trim is given by LCB minus LCG into final displacement upon MCTC into 100. LCB 72.255. LCG also remains unchanged. That is a concept. Why? Because we have not moved any weights after departure. Upon sailing from the dock, the LCG, which was equal to LCB, was 72.191. No weight has been moved after that. So the ship's center of gravity LCG will also remain unchanged. So 72.191. Displacement in salt water is 19298. MCTC in salt water 213.2 into 100. So I get the trim, final trim in salt water 0.058 meter by stern, because LCB is greater than LCG. So it is by stern, is positive answer. Then TA trim off will be total trim into LCF upon LBP. LCF in salt water at hydrostatic draft was 69.688. So trim 0.058, LBP 143.16, TA 0.028. TF will be total trim minus TA. 0.058 minus 0.028 is 0.030. So TA and TF is now applied to the hydrostatic draft at which the ship is floating in salt water 9.102. Because ship is trimmed by stern, obviously. Why? Because LCB is greater than LCG. So forward TF will be minus, TA will be plus 9.072 and 9.130. Let's draw the diagram and give the reason why it happened. Ship was at even keel in fresh water. LCB was equal to LCG at even keel. Okay, and the value was 72.191. 72.191 was the LCB. Now the ship is now in salt water. My LCB has increased to 72.255. So it was 72.191. It has now increased to 72.255, whereas my LCG remains unchanged at 72.191. So the ship's LCB has become greater than the LCG. In other words, the center of buoyancy has shifted forward. LCB is from off perpendicular, so it has become more now. That means the buoyancy has shifted forward from B to B1. Now the center of buoyancy and the ship's displacement, they have formed a couple. And this couple has a trimming lever which is equal to BB1 here. This couple will rotate the ship and trim the ship by stern. And the ship will continue to trim by stern till the time the center of buoyancy again comes under the center of gravity of the ship. So that was the explanation why ship has trimmed first of all, and ship has trimmed because LCB has changed. And LCB depends upon underwater volume, shape of the hull. So because the density of seawater has increased, it was in freshwater, density was 1, it is in saltwater 1.025, and mass, the displacement has remained unchanged, so the underwater volume has decreased. It has reduced, the ship has rise up parallel, thereby the underwater volume has now changed and the center of buoyancy also consequently changed. And because the ship's hull, shape of the hull, water plane area is changed, so we see that the buoyancy has shifted forward. This created a couple between buoyancy force and the ship's weight, and which rotated the ship to trim by stern. That is the explanation. Okay, I have the particulars here. You can also calculate yourself, and if there are any comments, you can put in the comment section. I will answer them. If this question is repeated many times in the past papers. Okay, thank you very much.